Seems you all recognize this site. And so, I know that most of you here have been through the Natural Science Building. If not, maybe you've traveled around Michigan. And so it may make sense to you that every day at work, coming in and out of the building, that it's not difficult, in the importance of understanding Earth's history and its importance to our state in general it's a constant reminder. And so I think that there's no better place to contemplate the history of life and what it has to teach us about our future, as well as the potential for habitable worlds even beyond our own, than lying across the 2.5 billion year old piece of Van Nuys formation from the Upper Peninsula. My research focuses on understanding the Earth's ocean and atmosphere chemistry and the ties that has to biological evolution. And this focus is really on the last 4 billion years, which Earth is 4.5 billion years old. And that's because the oldest known life on Earth extends back to 4 billion years ago, and that comes from chemical signatures found in ancient rocks. And a major focus of that research comes on molecular oxygen, which is a key player in this story. And so, even though Earth's first life was microbial, it didn't require oxygen for survival, and it lived in environments that were devoid of oxygen, the evolution of photosynthesis really shaped our planet in the preceding 3 billion years record that we have in the geologic record. And even the earliest and simplest animals require oxygen to survive, and as we do today. This area of research has overlaps with multiple fields, including future climate change. I apply geochemistry as my tools, Earth history and biological evolution, which I mentioned, as well as astrobiology, or the study of environments that may host life, extreme environments that host life, and the potential to find those environments on other planets. And so research like this is becoming particularly important even as we speak now. There was a recent launch of the James Webb Space Telescope, which is looking to characterize exoplanet atmospheres, and Earth's history may provide a guide to the types of places that we may be able, the types of environments that may exist outside of our solar system that could host life. Because there's been, as I'll show, dramatic changes in our own planet's atmospheric composition over time. And so, the truth is, however, though, that our planet is unique, and despite our best efforts and ongoing efforts, it is the only planet that we know of that hosts life. And therefore, it acts as our best point of study to understand a planet that does host life. And so you can tell that even from afar. So looking here at a spectra of Earth's atmosphere from satellites, you would know that there is abundant oxygen, that the Earth's atmosphere maintains water. It also has important greenhouse gases and gases that are indicative of biology, such as methane accumulating. And today, the abundance of oxygen in our atmosphere is something close to 21%. However, it hasn't always been that way. And that kind of gets at the key of my research group and some things we've looked at before and going forward here at MSU. So shown here is a curve of a reconstruction of atmospheric oxygen concentrations through time. And those are shown at percent relative to today's levels. And as you can see that there have, over the last 3 billion years, or at least 3 billion year record of oxygen accumulation, that there have been rises and falls, and throughout that entire time period, Earth has sustained life. Which means that each of these these past intervals could be an ancient atmosphere that could tell us something about life beyond our own in other solar systems, and tells us something about the limits of life in general. And our toolbox to put together quantitative curves like this for oxygen or other gases that accumulate in the atmosphere is shown here, and I've tried to highlight some things you can't, may be difficult to see, they look bolded here, such as vanadium, chromium, manganese, iron. You can see nitrogen, carbon, sulfur. One of my favorite elements, iodine, and these are elements that are reactive with oxygen, and that we can use their presence in the rock record to say something about past accumulations of oxygen, but also the effects of these kinds of environmental changes on their own biogeochemical cycles. And so the study of their isotope compositions and their concentrations in specific minerals and rocks, like atmospheric spectra of fossils, can tell us something about life in co-involving environments on early Earth. And so I do spend a lot of time scavenging the rock record, but actually a lot of this work involves studying modern analog environments. And so, these give us clues to the kinds of mechanisms that may drive the observations that we make in the rock record. And so what's driving these global changes? And so as an example, just last July, I spent time on the research vessel Falkor in an oxygen minimum zone in the Pacific Ocean, and where we performed experimental incubations to understand the oxygen limits of microbial metabolisms, very specific metabolisms, and to as clues to what may be driving changes in the same elemental cycles that are observed in some of these proxies that tell us about global change in the past. And so this is particularly important because though these environments are rare now, they likely represented, these anoxic environments or low oxygen environments, likely represented much of Earth's oceans for the first 4.2 billion years of its 4.5 billion year history. So they're just a sliver of the ocean today, but very important in the context of Earth history. And they're becoming more and more relevant because in combination with warming of the planet, there's observations that oxygen concentrations in some of these same oxygen minimum zones are decreasing, and these oxygen minimum zones are expanding. And so the past record of these kind of environments and the processes, the chemical processes occurring within them are really important at this time to understand the effects on the surrounding ecosystems going into the future. And so, as another another example of an analog environment, Dave mentioned at the beginning that I recently had the opportunity to travel on the human-occupied vehicle Alvin to about 1.5 miles below the seafloor to look at hydrothermal vent fields. And these are settings where superheated water is discharging from the seafloor. And again, they're a unique environment today, but they are thought to have had a very important role in ocean chemistry throughout much of its past, as well as potentially being a very important spot for the initial evolution of life itself. And so one piece of evidence for this is the actual banded iron formation that stands out front of our own natural science building, which is a testament to an anoxic ocean where iron-rich waters from hydrothermal vents were allowed to expand throughout much of the world's oceans and be deposited. And so, with that, I just want to finish by pointing out that going forward, our research group is working on applying and developing isotope tracer techniques to understand the processes driving these global changes that are observed in the past, as well as reconstructing these past environments. And a lot of this is going to be happening thanks to a new clean room, which is largely metal-free, that is under construction now in the chemistry building. And that I would like to particularly thank the students, faculty, staff, administration, donors who supported this lab, as well as my position, and who are supporting the research going forward in MSU. And I just want to say as well that I'm particularly proud and feel a sense of responsibility to have one of these positions, a Dow positions, and that I take it very seriously, and that I'm looking forward to being a leader within the department and helping the department maintain its status as leaders going forward. Yeah, thank you.